because we're going to do the, so far we've been just preparing, so to speak. Today we will deliver the punch. Okay, so we're going to prove the theorem, right? What theorem? So this is the main theorem of what goes by the name of character theory, right? So right, so let us recall what the character is. So we will assume, well, for this definition you don't need any assumption, so let me make a definition. So definition, G a group, V a finite dimensional linear representation of G over some field F. Right? Then by the character of V, this is a definition denoted chi of V, so which is also denoted like that. This is a function from it is an f valued function on G, and is a function defined by, or is the function defined by chi of V, its value on an element, it's a function from G to F, so I have to, it eats a element of G and gives out a element of F. So this is, what is this? This is trace of G sub V. Where G sub V denotes the matrix or the linear transformation on V corresponding to the element G, because linear representation means what? You have a map from G to GLV, a group homomorphism. Okay. So, and here is the point. So this is the definition. Is the definition of the character clear? Okay. Now here is so I'll state it as a sort of principle. Okay, the precise theorem will come just a little later. We have already stated it last time. I will state it again. Okay, the principle is the following. So here is the sort of moral, if you want. Let me call it moral. So let us take F to be C. Right, what will be important are the two properties of C, namely it has characteristic 0 and it is algebraically closed. But we will not, let's not for the moment worry about such niceties. Just let's assume F is equal to C. Even in this case, the proofs, the results are interesting, and this is the most interesting case. Okay, so let us just, we will, for character theory, when we speak of character theory, we will assume the field to be complex numbers. Okay. F to be C, G finite. So group is assumed to be finite. So here we assumed the group need not be finite, but to make sense of this, you assume that the linear representation of was finite dimensional. Okay, G finite, any finite dimensional representation, any, okay, let's say finite dimensional representation. We may not need this, but in any case, any finite dimensional linear representation of G is determined by its character. So, as we were saying, the character is like a fingerprint, right? After all, you are extracting what seems like a tiny slice of. Okay, let's see. Is this clear what we are doing? Okay, now let's state the theorem. Theorem G finite the characters of irreducible representations over C form an orthonormal basis for the Hilbert space of class functions on G with inner product space of class C valued, that is understood. The class functions are C valued, so that's a complex vector space, right? With inner product Fg is equal to this is the theorem. Okay, let us parse. There is a lot of things here, so let's understand what it means before we start proving it. Okay, so let's understand this Hilbert space of class functions. What is class functions? Functions that are constant on conjugacy classes of G. Okay, so the dimension of this space is more, obviously, evidently equal to the number of conjugacy classes of G, because a basis, for example, for this space would be a function that is what do you call it? A characteristic function of a conjugacy class, meaning it is 1 on one conjugacy class and 0 on all other elements. Okay, so it's 0 or 1 depending on whether an element of G belongs to this particular conjugacy class or not. Okay, so if I given a class, that would be the characteristic function of that class, and clearly those there is one characteristic function for every conjugacy class, and they form a basis. Okay, so the number of these is clearly, the dimension of this space is equal to the number of conjugacy classes of G. Okay, now it's first of all a vector space by pointwise addition and pointwise multiplication. Okay, as we pointed out last time, the functions on any set. Here, the fact to make this a Hilbert space, you don't need the fact that G is a group. You're only using the set structure of G here, right? You could take pointwise functions on any set with respect to scalar multiplication and pointwise addition. That's a pointwise scalar multiplication, pointwise addition. It's a vector space. Right, and you could give this inner product on that. This instead of X and G, just think of G as a set. Okay, even this is not required, right? It will make it an inner product. The reason why we have put this in, this normalization factor is required, is because otherwise in the theorem this won't be orthonormal. Okay, so this normalization factor is not important to make it a Hilbert space. Even without this, you will get that it is a Hilbert space. That's not a problem. Except that with this, the theorem becomes nicer because you will get an orthonormal set. Okay. Now, what this? So what does? Okay. So what? So is the Hilbert space clear? What Hilbert space we are talking about? Okay. Now, what we are saying is, now assume G is a group, finite group. Look at all irreducible representations over C. Right? We know what this means. These are representations, linear representations of G over the complex numbers. Right? All irreducible representations meaning, of course, up to isomorphism. I list each isomorphism class, right? And there could a priori be infinitely, possibly infinitely many, but we have already seen reason that this is not going to be infinitely many. But even if you don't know it, right, maybe we have not given a full proof of that because we used maybe Jordan holder, which you haven't proved, right? But so, so far you only had it on faith that there are infinitely many irreducible representations. But here now this theorem will actually prove it, because you are going to say that that number is equal to the number of conjugacy classes of G, and G is a finite group, so it's going to be finite. That's part, if you wish. We are not going to assume that it is finite. We are just going to prove that that it is going to be equal to the number of conjugacy classes. Is this clear? Okay, so the number of, for example, so we don't have the full proof yet that the number of irreducible representations is finite, but this will provide that as well. Okay, okay. Is this clear? So should we proceed to the proof then? Okay. Now to the proof itself, I want to point out that this is a very short proof, if you wish, but that short proof is worth spending a lot of time on, because it is worded in a language that is perhaps slightly higher than what you are so far used to. Okay, so let us just do the proof, and I encourage you to dwell on the proof. You should study the proof intensely. It will pay back, because the arguments used in character theory are all appearing in the proof. So it's a good proof to master. Okay, so you should sit down and maybe every day write down the proof. It's not a bad thing to do at all. Okay, okay. So, and the proof is very short. It's not that it is very long.
What is it that characteristic this case to class function? You are making an indicator function, like one
indicator function, or yes, yes.
But once you give the representation, so in each classes you have some number. How you can make it 0 or 1?
No, I am not saying that. I am not saying that the characters form such a indicator function. No.
But you are saying you can make it like in one class it is 1.
No, I was just saying if I take the indicator function of a conjugacy class, fix a conjugacy class, then they form a basis for this Hilbert space. That's all I'm saying.
How you get the representation that indicator function of the characteristic classes?
You will see that. You will. That is part of the proof. It will tell you how to compute indicator function. You should be able to write the indicator function as a linear combination of irreducible characters. That's what it means.
characteristic class
Hmm.
is going to be some numbers.
Yes.
So we find that number to multiply to that indicator of that class. That's what.
Yes, for example. So, yes, clearly the indicator functions form a basis. They may not form an orthonormal basis with this, but they do form a basis, right? Okay, they do form a basis. What we are saying is that the characters form an orthonormal basis, right? Yes. So that's the way it is. I mean, it's okay. So just to this theorem is about maybe 120 years old. It's late 19th century. Due to maybe, I don't know the exact history, but Frobenius, Burnside, maybe mainly Frobenius. This is due to Frobenius. Okay, so dating roughly from the 1890s. Okay, so here is the proof. Okay, let V and W be irreducible representations. These should be finite dimensional, right? Why? Because if I fix one V, we saw this argument the previous time also. Yeah, just take the orbit of V, that's a finite set that spans a G invariant subspace. If you have an irreducible space, then that must be the whole of the space. So these are finite dimensional. So it makes sense for us to talk about the characters of these, right? Okay. So these are finite dimensional because G is finite. That's an easy argument. Okay? Okay. So what am I supposed to do? Let me do chi V G chi W G right. This is what I'm supposed to compute, and I must show that it is either 0 or 1 depending upon whether V is isomorphic to W or isomorphic to W meaning as a representation, as a G isomorphic to W or not. Correct? That's one. Are we done if we do that? Not quite, because that will only show that the characters are orthonormal. To show that it's a basis, you will have to argue also that they span the whole of the Hilbert space, whole space of class functions. Okay, so there are two parts to the proof, if you wish. One is showing that they are orthonormal. The other part is showing that they span this space of class functions. But why? Okay, so that will show that any character is a sum of characters of irreducible representations. But here we are talking about class functions. You are right, but only, I mean, you are pointing out something that's good, that's correct. But indeed, if I take what Suraj is saying, suppose I take any representation, I know we are in a situation where we have complete reducibility. That is, every module is semi-simple, every CG module is semi-simple, because by condition 3, Marshke's theorem tells us, so remember the equivalent conditions for a semi-simple module. The third condition holds by Marshke, therefore, by the second condition, every representation is a sum of irreducible representations. Okay? Every finite dimensional representation is a sum of finitely many irreducible representations. Okay, this much we have. Therefore, and it's also easy to see that the character of, if I have a direct sum of representations, then the character will be the sum of those two. Right? That's not very difficult to see. We'll make a list of the properties of the character. Okay. Tensor will be product and so on. Yeah. So let's just for a minute. Let's we'll need to list that for the proof anyway. Okay. Okay. So so chi of v will be, if v is equal to not this v but some general v is equal to vi to the ni, then of course chi of v, the character is sigma ni chi vi or chi I, let me write, right, where chi I is chi vi. That's okay, that's not a problem. We are still not done, because what we don't know. So indeed, any character is the sum of irreducible characters, but we don't know that it would still be not clear that every class function can be written as a character or a sum of characters, meaning, or as a linear combination of characters, to be more precise. If you could show that a class function is a function, linear combination of characters, then you would be done. Okay? This is clear? Okay. We have said class function. Okay. So let me give you the proof first, and then I'll list out the steps. We'll list the steps on the side. Okay. The steps are, you will need to observe some small bits. Okay. As you might have observed, when I say a proof is short, it means that there are several things that I am pushing under the carpet. Okay. So let us again I do the same. I claim that the proof is very short. I will write out the proof, and then the justification for every step will be given separately. Okay. No, there is a reason why I say this, you should understand, is that many of these smaller steps are actually, for example, chi of v plus w is chi of v direct sum w is chi of v plus chi of w. That's a trivial statement. Okay, it's just a checking. It is not a theorem, whereas this is a theorem. Okay, so it is once you are familiar, or sorry, once you know the definitions, so those matters, those that are just matters of unwinding definition. One seeing this, looking at it this way, that way, that is just modulo that, right? What is involved in the proof? Okay. So let's write this. So first step is to write this as, okay, so okay, so let me so first step, I am using the fact that chi v bar is equal to chi v star. We will come to that, but let's just understand that statement abstractly. We will worry about the proof of that later. Okay. So what does this mean? What does this notation mean? Chi v is a function, right? What does bar of a function mean? I just look at the image and map the, instead of taking it to that element, I take it to its conjugate element as conjugate complex number, right? That makes sense. So this is a class function. By the way, it's clear, last time we saw characters are clearly class functions, right? Though there is no, okay, so that's, characters are clearly class functions. That's part of the, that's, you have to, okay. So this is a class function, and taking the bar is also a class function. Okay, so this class function is equal to, what is this? Now V star is another, the dual representation. That is the space of linear functionals on V, that becomes naturally a G module, right? Or KG module or CG module, and it's a finite dimensional representation. So you take the character of that. What is the relation between the two? Well, the claim is that one is the bar of the other, right? So this, you're blocking the Avijit, maybe you should sit here. How about, okay? Right. So that's first one step. Okay. Now let's use what Avijit said, right? So here, this is a product of characters. This is the same G. So this is a pointwise multiplication of two characters, right? So this is going to be the character of V star tensor W. So this is right? Okay. Now, see, once you see this, something should already start ringing bells. Namely, what are we doing? You're taking trace of some linear operator on V star tensor W, right? And there is a sum. Now, you can take this out, right? So, I'll write this. So here is second one. Why? So instead of stating with V star, let me write it like this. Right? That's something I'm using that to go from here to here. Yes, yes, indeed, but that is one step later. Yes, yes, indeed. We'll come to that in a minute. Yes, correct, absolutely correct. So this is equal to, let me write. I can take this to the. So what we are doing is, right? Okay, now let us write one more line here. That's equal to, I'm continuing here, is equal to trace of, let me write it like this. See, I want you to be comfortable with the notation, the way it is being thought of. Right? If you are not understanding something, please stop me. I don't mind explaining it twice, 3 times, 10 times. I don't mind it at all. Okay? So the proof of this theorem given in textbooks is, I don't think there can be 2 different proofs. All the proofs are the same. Okay? Except that very few, since this kind of proof is done in rather elementary books, meaning where they don't want to talk about words like Hilbert space or inner product or tensor product, etc. So they avoid these terms, and therefore the proof looks different. It is just the same proof. You know, if you unwind this and write it without tensor product, without something, that's how it is written. Okay, it's about time that we stopped, you know, sort of saw through those proofs and thought of the proof this way, in my opinion. That's why I'm doing it this way. Yes. Okay, that's a good question. Okay, what does this mean? What does this mean? Well, this actually doesn't make sense. Here, Krishanu is right. This doesn't make sense yet, but we can make sense of it. Right? What is this? This is a function on G. But I am thinking of it as a function on an element now of, if you want, of the group ring. For example, you know, this has several meanings, as we say, right? Depending on the context, I will just interpret it to mean the right thing. So let me interpret here to mean the group ring. Well, that comes from the following fact. If you have a map from G to C, G to any vector space, look at CG, the group ring. This is the free vector space spanned by elements of G. Therefore, whenever you have a map from G to C, you have a linear map unique linear map that extends it from CG to C. So this also makes sense as, if I have some function here, I can also write the same notation and write that function there. The same notation makes sense because there is a one-to-one correspondence between the functions here and functions here. Linear functions here and functions here. Right? Okay? Is that satisfactory? Correct. But this is precisely the kind of thing I want you to do. Right? Think of it, you know, does this make sense? Well, it does not. Literally, it does not. Okay? So do we give it up? No. We, you know, because the point of this, writing this, is the calculus of it. You know, this is an important thing. When you see this, there should be certain, you should react. Like when you see cos square theta plus sin square theta. No? That's a reaction, right? Or e to the I theta. You immediately think of it as cos theta plus I sin theta. Right? It's just a reaction. It's just a reflex. Similarly, you should develop a reflex for this. When you see this, that's a certain element. Okay. So, is this?
And the one way you have also said that G acting on G acting on W, so G will act on G will start and
Exactly. G will act on. Absolutely. That's what I have written here. This here it means. Here it means exactly what you were saying. Action of G on V star tensor W. So that's a linear transformation or even a matrix if you wish, and it is the trace of that matrix. Okay? So what here we are doing is that the fact that the trace is a trace is a linear map. So the trace of a bunch, see here what we are doing is adding the traces of certain set of linear transformations and dividing by a scalar. Now I can just add those linear transformations, divide by the scalar, and then take the trace. Okay? So if you want, you can leave this step. Okay. If you want, you can just directly go there. Okay? You need not worry about this. It's okay to write this, but you can just go. Is this clear? But finally, this is equal to that. Yes, we'll come to that. Yes, exactly. That's the next step. That's the next step. Exactly. Yeah, exactly. Absolutely. That's what we are trying to at. Yes. But that's the next step. But is this okay so far? Okay. So what have we done so far? We've used this, and then just rewritten something. It's just use something on the linearity of the trace map. right? Okay. Okay. Now we will do what Avijit was just mentioning. What is this? See, I keep saying that there are only two things in this. One is averaging, one is Shor's lemma, right? Those are the only two ideas, right? Of course, not counting any of these. These are just calculations. Okay, what is this? So, in fact, recall. So here is. I'll write it here. So this is something we have done, right? Okay. So averaging. What does it do? If I take 1 over G and sum over G sub V of G, I'll write a V here. We will apply this to V star tensor W. Okay, but at the moment I'll write it V. Okay. What is this? This is projection onto VG, V upper G. That is those elements of V that are fixed by all elements of G. Right? So this is the formula for averaging, right? That's what the averaging does, right? Okay. So now what is that? Instead of V, we have V star tensor. Okay. So this is trace of projection to V star tensor W G. Right? What is the trace of a projection map? The dimension of that. Okay, let's observe that. So let's write that here. So maybe I can erase this because I didn't need this step anyway. So here, so trace of a projection is equal to dimension of the image. Why? Because see, what is a projection? It's a map from V to itself, if you wish, whose square is itself. Right? Okay. So now if I take, if W be the image of that, if I write, just elementarily, if I choose a basis for W, then extend it to a basis for V, and write the projection, the matrix of the projection in terms of this basis, what do I see? For the corresponding to the elements of W, I'll see identity here and 0 here, because every element of W goes to itself. What do I see here? Of course, any element of V goes to some element of W. So there could be a star here, but surely it is 0 here, because these are the other elements of V, right? No matter what basis you choose. Right? Here I am not assuming anything about the existence of a complement to W or anything like that. This is just, right? Nothing like that. So then the trace of this is obviously 1 plus 1 plus 1 plus 1 as many times as the dimension of W. Right? Okay. So, is that okay? Okay. Right. So what is this? Trace of a projection is equal to dimension of this. Right? Okay. Now, what is V star tensor W? G. we said that V star tensor W is equal to form V W. Yes, you can write a C here, but I will not write it. This is as a G. This is a G map. This is a representation of G. That is, if V and W are representations of G, then V star is naturally a representation. Tensor product is naturally a representation. So you make this into a representation of G on the one hand. On the other, we have also seen that maps from V to W form you can put a G action on that, and the linear maps from V to W will become a linear representation of G. Okay? These two representations are the same representation via the standard isomorphism that you know between these two spaces. Of course, assuming V is finite dimensional, but here everything is finite dimensional. Right? Okay. So you can write this. This is dimension of course, this is like this, right? Dimension of form V W G, right? Yes, but this is equal to, okay, one more. Okay, I didn't give myself enough room. Okay, so we'll proceed here. So can I erase this? This is the trivial fact that, this just means that G, G of phi, which is phi, G phi, G inverse is equal to phi. This just means G phi is equal to phi G. Both are equivalent. Okay, so this is, okay. So you can write this as form G V W dimension. Okay. So let's see, let's start writing. So this is averaging. Right, this is this fact. Okay, so you can trace each of these equalities to one of these facts there. Okay, but what is this? V and W are irreducible representations. If V is isomorphic to W, how many G maps are there? Only the scalar multiplications by sure. If V is isomorphic to W, then there is only, there is only one dimensional. See, it's a division ring by sure. This is a, it's either the zero map or an isomorphism. Correct. Moreover, that's one fact. But moreover, suppose you have one isomorphism, then any other isomorphism must be a multiple of that isomorphism. Okay. Maybe we haven't stated it this way, but this will follow, because if I have one isomorphism, see, what we have seen is that end GV is equal to C. That's what we have seen, right? This way, so you can just take it as a homework that if I have, but here we are talking about V and W. If there is one isomorphism, you can use that isomorphism to identify Hom GVW with end GV.
But sir, V and W are irreducible, right?
V and W.
Like any representation, I mean, we are working on C. C is a repetitive case, so any operator has an eigenvalue.
For that to make sense, the operator must be from a space to itself. That's the problem. Yeah, you're right, but you can identify. I mean, that's so fix an isomorphism, identify W with V with respect to this isomorphism. Then you can think of Hom GVW as end GV, and then it's the same as Yeah, so there is a little bit of thing maybe to be seen here, but the point is the fact that NGV is equal to C means translates to, if I have V is isomorphic to W, then V and W are irreducible representations, then any other isomorphism is a scalar multiple of a given isomorphism. Okay? So by sure, so this is sure is 0 if V is isomorphic to W, oh sorry, 1 if V is isomorphic to W, all right, first part done. Any questions? Okay, already from the first part, you see several things. Corollaries. Okay, so let's see. This is okay. Sorry, I switched. I'm just looking back at the proof and seeing which ones, to complete the proof, we have to tick all of these, right, one by one. Okay, let's see. Maybe we should do that before we talk about the corollaries. Okay, so this is okay, right? This is okay. This we just saw a proof of. This is okay. This, of course, we talked about this, right? Okay. This is rather easy to do. Okay, let's okay, before we do this, let's stick those two. Okay. So, how about this? Okay. So, so I want to say that a trace of phi tensor psi, if phi and psi are in end V and end W respectively, is equal to trace of psi times trace of so this makes sense. If phi is in end V, is a linear transformation from V to V, phi is a linear operator on W, then this is a linear operator on V tensor W. Okay? Right? This is a triviality as follows. So, okay, so fix a, you can do this by as follows. Fix a basis for, fix basis Vi and Wj for V and W respectively. I will not write that out, okay, in the obvious meaning given to these symbols. Okay. Now, Vi tensor Wj base for V tensor W. Okay. So what does phi so what matrix of phi tensor W is matrix of V tensor matrix of psi with respect to appropriate basis. Okay, so that brings us so what is the tensor product of two matrices? Have you seen that before? No. Okay. So you unfortunately again this is something that yeah. So the tensor product of two matrices is defined this way. So A tensor B. Okay. Again I forget what is the standard notation. Is if I have m by m, n by n. The reason why it is not defined is it's because it's defined in terms of with the tensor product notation. So you know you don't really need to know this, but you know you can sort of rationalize it, work backwards, and understand that the tensor product of matrices is really the tensor product of the corresponding linear transformations. Yeah. So it's an m cross n matrix, right? So let me write it like this. So if I have A tensor B, so this is m cross m, this is n cross n, say. Okay. They may be more general, but we are just doing the generality here. So I take A11B, just multiply so this is I'll write A1MB. Here I'll write AM1B, A21B, A2MB, AMMB. So each one is this is an m by m block, sorry, n by n block, right? It's an n by n block. So if you work out the matrix of phi tensor psi in an appropriate basis, either Vi, you know, it's a question of ordering this. Do you want to order this first by, you know, there are two natural orderings. You can first keep this constant and vary this, or keep this constant and vary this, right? So there are two orderings. Depending on the ordering, you will get either this or the other way. You could also could have written B11 A and so on, right? Okay, but what is the trace of this? Well, A11 B11, that's the diagonal element. Here A11 B22, so on, right? So here the trace is A11 times the trace of B. Here it is AM times the trace of B. You take trace of B common and you get trace of A times trace of B. Okay? So this is just a mere calculation. Correct? Okay, let's do this one. That's perhaps the most interesting one. Okay. So matrix, sorry?
Matrix of phi tensor psi into matrix of phi into matrix of
Tensor, not into. Into doesn't make sense. Right? It's an m cross m, this is an n cross m. So into doesn't make sense. Into would be composing, right? Composing those linear transformations. That doesn't make sense in this case. Need not make sense. Here it is the tensor product. Tensor product is from is an endomorphism on V tensor W. Right? It's a much bigger matrix. It's a Mn times Mn matrix. Okay?
So sir, you are saying A tensor to be two matrices looks like this.
Yes.
Some basis.
Well, I don't remember how that is defined, in the sense that whether I should write A11B or B11A. Yeah, one of these two. I don't know what the standard definition is, but
But this is the definition of A tensor matrix.
yes, you can. If you look at Jacobson basic algebra, for example, basic algebra 1, I believe before even defining tensor product, they defined tensor product of vector spaces. So there is also tensor product of matrices. Yeah. So if you have time, I would suggest you read that, because normally tensor products are introduced with complications, but here all our tensor products are over vector spaces. So that's a much there are no subtleties there, so to speak. Okay, tensor products over more general rings, which we will come to when we do a little bit of commutative algebra, for example, or for that, tensor product can be over arbitrary rings. I mean, you have to define it appropriately, left, right, something. But over, here we are over a field, so it's especially simple. You know the dimension of this. It's as a vector space. It's the dimension of this. It's just the multiplication. Yeah? The dimension of that is just dimension of V times dimension of W. All right. Okay. So let us do this. That's interesting. So I'll give you a minute. There is one particular statement that we have said, which is not averaging, which is not Schur's lemma, but something else. There was some other word that we used, something that we said, which is relevant to that. I'll give you 30 seconds to guess the word. Okay, I repeat the question. We want to prove this, right? So to prove this, what is relevant is some fact other than Schur's lemma, other than averaging. There was some other fact that we said, that we actually showed is true. G is fine. Yes, G is fine. Yes. So what is the word? What's the word you want to use? Unitary is the word. We have proved that it's unitarizable. We proved that every representation of G is unitarized over the complex numbers, of course. We are talking about unitary matrices, is unitarizable in the sense that you can, if I write out matrices for any finite dimensional representation of the complex numbers, I can always find one particular invertible matrix and conjugate all these sets of matrices so that all of them become unitary, because the reason is because you can fix an inner product and then average this inner product to get a G invariant inner product, and if you write choose an orthonormal basis for that G invariant inner product, then express all your matrices, all your linear transformations with respect to such a matrix, they will be unitary. That's the reason. Okay, going through the proof. So what is relevant here is the unit. See, okay, I'll tell you what. So G. Okay, here is the rough idea. We'll write out an exact proof. How does G act on? What is the action on B star? G of f of V is f of G inverse of V. There's a G inverse there, right? If for a minute, if G is unitary, what is G inverse? For a minute, let's be a little loose. If G is a matrix now and it's unitary, what is G inverse? It's star. What is the trace of its star? Bar, because it's transpose inverse, transpose conjugate. Transpose does nothing to the trace, the conjugate does, take bar. That's the proof, really. That is the way they used to do it in the old days, right? If you have a matrix representation, what is the, so to speak, okay, so let me say it here. So, fix a basis for V with respect, so fix a basis for V okay, which is orthonormal with respect to a G invariant inner product on V. Okay, let's see if that makes sense. Right, that's why here this is another way of saying it. What I do is, given a representation, I choose a G invariant inner product on V. I can do that because I can take any inner product and average it to get a G invariant inner product. Okay. Now, then I choose an orthonormal basis of V with respect to that inner product. Okay. Now what is the, now every element of, with respect to this basis, every element of G looks like, I mean, if I write out the matrix of the linear transformation, it will be unitary. Okay. So, elements of G with respect to this basis, inga ezhudalama. Okay. Now, choose for V star a dual basis. Okay, so or let's make a fact. Okay, I want to make this fact. Again, this is one of those elementary things which you should definitely work out. No matter, I know, this is not the kind of thing I should be giving the proof of, because writing this on the board does not make any, if somebody wrote it in front of me on the board, I wouldn't understand it. I would have to go home, sit down and make sure I write out a few things and understand it myself. So I'll write out the fact. The proof is an exercise. You just have to convince yourself of the following fact, that here is the fact. So let V be a representation of G. So it's a finite dimensional representation of G. Let V star be the dual representation. Okay. Fix a basis for V and okay, let GV right. So this fixes a dual basis on V star. Right? Okay, here is the question. I take every element of G is represented by a matrix with respect to this basis. Right? Okay, I write that matrix. So let GV, so let's call this B. Okay, let's call this dual basis, let's call this B star. That's just notation. Right? Okay. So GVB, what do I mean by that notation? GV is a linear transformation on V. I write it as a matrix with respect to the basis B. So that's a matrix of size dim B cross dim B. Right? Okay. I can also look at G of V star. This makes sense, right? If G is this is the dual representation. That also makes sense. So this is a linear transformation on V star. That's a matrix. Right? What's the relation between these two? First star, huh? Okay. What does star mean? But suppose I have not assumed that my field is complex numbers. This is general field. It's a field is arbitrary. This has nothing to do with complex numbers. What does adjoint mean? You need an inner product. So what do you mean by adjoint here? See, this is a matrix, this is a matrix. Tell me what the relation between these two matrices is. This is a matrix, that's a matrix. How do I find the adjoint of a matrix? To my understanding, an adjoint makes sense if you have an inner product or some kind of form or something like that. Okay. So my question is, okay. Adjoint, by that you mean just if I take phi, then there is a phi star, the dual of a linear transformation. Okay, fine. Okay, in that sense you can define it. Okay, fine. That is fine. But here is the matrix. I mean, this matrix I write out. What's the relation between these two matrices? This is the question. No, they are not similar. Exactly. The complex case itself, they are not similar. They are conjugate. Okay, so let us think of this. Okay, I'll give you a guess. Okay, so here is the answer. Okay, let me tell you the answer. So this is you can put an inverse here or here, doesn't matter, because this is a representation. Okay, so I'm writing too small. So the relation between this is, so let me just give myself a little more room. So I'm saying inverse transpose. That's a calculation. Okay, I'll tell you roughly why this is. I'll give you a proof, or rather way to remember perhaps. is, what did we write? G of f is equal to f of G inverse, right? So that inverse accounts for the inverse, okay? And you want to make it a transpose because somehow it's see, if I just write an inverse, it's not even a, see, this is a homomorphism, this better be a homomorphism. See, if I take G V star and H V star B star, if I multiply them, then that must be G H of, see, this is a matrix representation. So this is a matrix linear, this must be a group homomorphism. If I write a inverse there, that's not a group homomorphism. So you better take some, it's an anti-involution, sorry, anti-homomorphism, right? GH of inverse is not G inverse H inverse, it's H inverse G inverse, right? So sort of to undo that, you have to do a transpose. That's one reason to remember, okay? But really, there is also a right-left problem in the sense that naturally a left action on V star, on V, becomes a right action on V star very naturally, okay? But then to make it again a left action, you need to put a transpose, okay? Anyway, so this is a, never mind, you know, even if all that I have said is sort of gas, meaning hot gas, I mean, you can forget it. This is just, this fact makes sense, right? Okay. Clear? It's a, and you can prove it just by doing a calculation. Okay? So, prove this exercise. Okay. Now why is this relevant to what we were doing? Now, if I take trace on both sides and choose my basis such that this is unitary, right? What is inverse transpose? Conjugate. And then I get what I want. Okay? So, this chi V bar, so this is one fact. So fact 1, fact 2 if you wish. Fact 1, fact 2, follows from facts 1 and 2. Right? So what I am saying is, look at this. We have this. This is for any basis. Here there is no complex numbers. Right? This is, we are making this statement for any field F. Okay. So you take this fact. Now you have this fact, combine these two facts. Now I choose my B such that, now you are over complex numbers. You choose my B so that B is an orthonormal basis for a G invariant inner product on V. Then this is a unitary matrix, right? I am taking its inverse transpose. Unitary matrix inverse transpose is just its conjugate. So this side is the, this becomes the, if I take trace, this becomes the conjugate of, and this becomes this, because I am just taking conjugate, I'm taking, I'm just taking trace, and trace with respect to, this does not matter. You can write any B here, any, you know, trace of this is precisely, by definition, this. Okay? This is an exercise. Okay, are we done with the proof of the first part fully? Okay, so there are several things. This is perhaps the one that is most interesting, and that here you have facts 1 and 2. Here is something for you to check and convince yourself and make sure that you understand. It's a good exercise because you'll have to write out, you have to unwind the definitions, right? You can write out an element twice proof of this, right? You can write, write this matrix, its ijth element, what it will do to a basis, right? You can just, if you write out the proof, it is just a few lines of, this is a matrix. You can write out the ijth element of this matrix and the ijth element of this matrix and see what you see. Okay? Of course, you can put the inverse here also. That may be easier. You can, you don't have to take the inverse here. You can take the inverse here. Right? I mean, because a transpose inverse commute, you can put it on the other side as well. Okay. And then this we had seen earlier, this was elementary, this is again an elementary fact, this we have seen earlier, this we have seen earlier. Okay? Now, we still have not done with the theorem yet because we have only done with the first part. We have now to prove that indeed every class function can be written as a linear combination of characters. That's what still remains to be done. But before that even, let's do a few corollaries of this. Okay, already this first part. The first part already has several corollaries. So corollaries. So given finite dimensional representation V, so as always, so G finite, F is equal to C, base field is C. God. Okay, given a finite dimensional representation V, so if V1 Vn is the list of isomorphism classes, is a list of irreps, so there are only finitely many irreducible representations, right? Because they are orthonormal. Their characters form an orthonormal set for a finite dimensional vector space. So there can't be infinitely many of them. Already, we don't need to prove the second part, right? The second part will show that they are actually a basis, but that's, never mind. They are an orthonormal set in a finite dimensional vector space, in a finite dimensional Hilbert space, right? The number of orthonormal elements, I mean, they are linearly independent. Orthonormal elements are linearly independent. So how can you have, if you have a finite dimensional Hilbert space, then the number of orthonormal elements is bounded by the dimension. So it's already bounded, right? Okay. So you choose. So this is a finite set. You choose it. Is the list of irreps. Then if I write V as a direct sum of, so we were wondering if, okay, every element of V, every representation V can be written as a direct sum of some copies of V1, some copies of V2, some copies of Vn, right? This is by Mashke, or rather by Mashke and the equivalent conditions for a semi-simple module, right? Mashke's theorem tells you that every G submodule has a complement. So then we have shown that that is equivalent to saying that it can be written as a direct sum of simple modules. In other words, direct sum of irreducible representations. Now this is the full list. So you will be able to write V as V1 plus V1 plus V1 so many times, plus V2 plus V2 plus V2 so many times, and Vn plus Vn so many times. Okay. Now here comes the question, and as we said last time that it is suppose okay, here is the question. You write it one way, I write it another way. Question: if there are 10 V1s in the way you write it, should there be 10 V1s in the way I write it? Yes, but why? Okay, so actually that is true, and we have not yet proved that, so to speak. Right? It is true very generally, but here you get that for free in the sense that, see, V is equal to V1 direct sum. What you do is chi V, you take the, see, if, okay, here is, okay, let me write it here. The number of times this appears is exactly the inner product of the character of V with the character of V1. So, indeed it is unique, whether you write it, so you understand, right? See, if you write it, say A1 times, then chi V will become equal to A1, chi V1, etc. But these are orthonormal. Therefore, they are linearly independent. If you write chi V is equal to A1 chi V1 and I write chi V is equal to B1 chi V1, etc., this A1 must be equal to B1. Right? If I have an orthonormal set, they are linearly independent, so they cannot be two different expressions for the same element of the vector space. Okay, so this is, so the uniqueness also is clear in this. We don't have to worry about the general uniqueness. So yeah. Okay, chi V, so V is irreducible if and only if, so a finite dimensional representation V is irreducible if and only if chi V is 1. Okay, okay. Let's apply this to so is this clear? Now, of course, if V is irreducible, then chi V is 1 because that's part of the theorem. Right, that's an orthonormal basis. So, but if V were not irreducible, what would it mean? It is some integer times V1 plus some integer times V2, etc. Right? So, what is chi V by this? Because, so if you want a proof, chi V is equal to, if I use this, it is, yes, so it is the square of this, right? see, what is chi v? So let's write chi v. What's chi v by this? It is chi v1 plus chi vn, chi vn. If I take now inner product, I will get the square of this plus the square of this plus the square of this. So chi v is the square of the following integers. So it's chi v1 square plus dot 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 plus chi vn square. Okay, good. So to say that this is 1 means that only one of these is, these are all integers, mind you. These are integers. Because they represent the number of times the representation occurs, the irreducible occurs in that dimension. So okay, now even more interesting, let's apply this to the regular representation. So let's give it a name. Okay, let V be the, or let CG be the left regular representation. Yes. Why? Because see, y integers. Okay. So chi v. So v is equal to v1 some a1. You can do this, right? Then chi v is equal to a1 chi v1 an chi vn on the one hand. But then because these are orthonormal, it's also true that chi v. So now if I take inner product with chi v1, all these are 0. So I get chi vj is equal to aj. So aj is, this is an integer, and therefore chi vj is an integer for every. Yeah. Okay. Now with respect to the left regular representation, let's see. So how do I decompose this? So I have to compute, to see how it decomposes, I have to compute. So let's see how this decomposes. Let's see how this decomposes. Right? How does this decompose? Well, I have to do this, right? I have to compute this, right? Okay. Let's compute chi of CG. Let's actually compute chi of CG, meaning this is the character of CG, right? So let's do it on G. Okay, that's an interesting exercise. Let's do this. We can do this just by, without writing anything, just by thinking. What am I supposed to do? I'm supposed to take a basis for this. Let us just do it from definition. I take a basis for this vector space, write out the matrix of G with respect to that basis and take its trace. Now, what is the basis for this representation? Elements of G itself. how does G act on them? It will permute them, right? If you look at this matrix, what is the shape of this matrix? It will be a permutation matrix. Will it ever take anything to itself? G1 is equal to G1 anytime? No. Except for G equals identity. So, for G, diagonal will be all zeros for G not equal to identity. So, what is the conclusion? It is 0 if G not equal to identity, and cardinality of G if G equals identity. Okay. Now let us do chi Cg chi V1. Is equal to, let us do it from the definition. Okay. So, this is 0 except when G equals identity. So, when I get G equals identity, so I can write that. So, 1 over G. So, G equals to identity I can write. So, when it is equal to identity, what is this equal to? Cardinality of G, cardinality of G bar, right? I can remove the bar, but for a moment let it be there. What is chi V1 of G? So, G is identity now. So, identity matrix goes to the identity matrix, identity element goes to the identity matrix. What is the character of the identity matrix? It's a trace. I mean, what is the trace of the identity matrix? Dimension of the vector space. So, it's dimension of V1. So, this is dimension of V1. So, what is the, how does it decompose? So, you get this following beautiful theorem or conclusion that Cg is V1 appearing as many times as dimension of V1. Each of the irreducible representations occurs and occurs as many times as its dimension. So, yes, so this is assuming V1, Vn are a complete set of irreps of G over C. Of course, that's right. Okay. Now, one more corollary is that the cardinality of G, therefore, taking dimensions on both sides. What is the dimension of this? The cardinality of G. What's the dimension of this? Well, dimension of V1, but that occurs dimension of V1 times. So, that's like dimension of V1 square plus dot 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 plus dimension of Vn square. Its square is bounded by the cardinality of G. Okay, so it can at most be square root of, I mean, that's a very, maybe even that's a stupid bound, but yeah, but its square is bounded by the cardinality of G. Okay, so now let's do Okay, maybe we should finish the proof. Next time I will talk about character table. Okay, but maybe we have just time for the okay, let's do the second part. Let's finish the proof. Okay, so that at least the theorem is complete. Okay. There is more to be said. We will take that up on Thursday. Okay, so let's completion of proof of the theorem. The theorem meaning that our basic theorem that irreducible characters form an orthonormal basis for the Hilbert space of class functions. So what is remaining to be proved is that given a class function, yes, it is a sum of that the irreducible characters form a span the space of class functions. This is what we need to do. Okay? Okay. So here is the idea. So okay, suppose that f is a class function, or should we call chi? Are you comfortable with calling chi a class function? Right? Chi looks like a character. Of course, at the end of this, it's okay because every character will be a linear combination, every class function will be a linear combination of characters. But for the moment, so this may be a little confusing because we have not proved that yet, but nevertheless, let me be bold and call it chi. Suppose that chi is a class function. Okay. Now I want to say it's a span of the irreducible characters. Okay. So let's assume that enough to show, so which is a class function that is orthogonal to the subspace generated by the characters. See, we've seen that every character the space generated by the characters is a subspace, right? Is a subspace of class functions. Every character is a class function. Therefore, the space generated by the characters is a subspace of class functions. Okay? Now, what we want to show is that, okay, so here is the space of all characters, space of class functions. Space of characters is a priori a smaller subspace. We want to show that there is nothing there which is not in here. So we will show, it's okay if I assume, since I'm going to use the inner product, I'm going to say take something that is orthogonal to all of this. In other words, I'm going to show that the perp of this subspace is 0. That's good enough. If I have a subspace whose perp is 0, then it's a non-degenerate form. If its perp is 0, then that space must be the whole space. Okay? So enough to show, suppose we will show chi is 0. This is good enough. Okay, chi is 0. Okay, how do you show chi is 0, right? Okay, so here is the idea. So it's a clever proof which will use several facts, again quite important. So what we will show is, okay, here is the idea. So again, this is a construction. This is like in geometry, you make a construction, right? So the following construction is here. So consider, once you see a class function, you should immediately think of the following element of the group ring, right? Consider chi g bar g sum, maybe with even a 1 over g, but doesn't matter. This is an element of right. So I want to show chi is 0. I want to show, therefore this element is 0. Okay, that's the idea. Okay, now okay, now what I want to do therefore is show that claim this operator so this is G in G as an operator on any representation V is 0. This is the claim. So you want to show, okay. Now how does this claim prove the theorem? Right. So it acts on the representation CG. So modulo the claim. So for a minute assume this claim. Modulo the claim. Modulo claim. We are done. Because look at this operator. How does it operate on CG? On the element. So this chi g bar, g acting on 1, this is in CG. So think of this as an element in CG. What is it? This is just this element of CG. But if an element of CG is 0, acting on 1 is 0, so this is 0. So this is equal to, on the one hand, it's equal to 0 on the other by claim. This is by claim. But then this, so comparing this with this, because G forms the basis of CG, you will show that chi G bar equal to 0 for all G implies chi is 0. Right? And here is again the proof is to show something is 0, some function is 0. Okay. Here indeed I am thinking of chi as a function and then sort of cooked up an element of CG based on that function. Right? Okay. So how do I show that this operator is 0? Well, here is another trick. It's a linear operator, right? To show that a linear operator is 0, okay, here is one more important observe. Okay, proof of claim. Okay, proof of claim. Okay, may assume. Okay, before no, I'll do the may assume later. Okay, note that. Note. So far we have not used the fact that it is a class function. Why is it so crucial that it is a class function? Well, the important thing is, look here, when I write thing like this, it is in the center of, it commutes with all elements of G. Because if I put a, so what does it mean to say it commutes? I should do, it's the same thing as doing HG H inverse. See, to say an element commutes, I multiply by H on this side, H inverse on this side, and show that it is equal to the same element. If I multiply by H on this side and H inverse on this side, right, I can then, because this is a class function, I can put the H and H inverse there, and then by just doing the dummy, choosing another variable, I can do this. Okay, so this is, note, because chi is a class function, chi G bar G belongs to end G of V. That element commutes with all elements of G. Okay. Now, okay, to show that it is 0, I may assume that V is irreducible. If I show, because to show that a linear transformation is 0, I can show it's 0 on every irreducible piece, and you're done. So may assume, now may assume, okay, actually I don't need that. Okay, no, I don't need that. Okay, sorry, I don't need that. I may assume V is irreducible, but I don't need that. What I can do is now, okay, by sure, okay, maybe, okay, I'm going back and forth. So may assume V is irreducible. Okay, let me assume that. Because it will be piece by piece, and on every piece, if I show it is 0, I am done. Okay. Now, this is a end G of V. So what does sure tell me? This is just a scalar multiplication. So this is just a scalar multiplication. By sure, so let me write it here. By sure, is a scalar multiplication. Say by lambda. Okay. So now you have a linear transformation that is multiplication by lambda. You want to show that lambda is 0. Suppose I take trace of that. Okay. So if I take trace of that linear transformation, since it's scalar multiplication, what is it? This is equal to dimension of V times lambda, right? But this is equal to what is the definition of chi times chi v? If I put the trace here. So, okay, let me write one more trace. So, this trace I can write as sigma g in g chi, so this is equal to chi g bar chi v of g. This trace I can put, okay, this is trace of g. I can write this. Okay, now that I can write as sigma g in g chi g bar chi v g. Now that's equal to 1 over g, sorry, g times 1 over g, multiply and divide by 1 over g, and then write this. But this is equal to g times chi v, but this is 0 by, again, by hypothesis, because it's orthogonal to all the characters. Okay, so the fact that it is a class function means that this operator is a scalar. By sure, that it belongs to NGV. The fact that this is a class function means it belongs to NGV. That's a calculation. Now, by sure, that's a scalar. Now, in order to show that that scalar is 0, you will take the trace of that. Yeah, so here is a important thing. In order to show that a scalar, scalar matrix is 0 over characteristic 0, you can equivalently show that the trace of such a matrix is 0. This is an important. This comes up again and again in many things which involve characteristic 0, right? To show that a scalar matrix is 0, you will show that the trace is 0. Okay. Okay. So so that's what we are using here. We are, instead of showing this is 0, we are showing its trace is 0, right? And so the trace, because that trace is just dimension v times lambda, this is a number which is, here we are using the fact that this is characteristic 0, right? So, and the trace is 0 because of the other hypothesis, that it is orthogonal to the space of characters. Okay, that finishes the proof. Okay, now what we will do next time briefly is that follows now. That now follows. That now follows from the theorem, because you know that they form an orthonormal basis for the set of class functions, and the space of class functions is clearly the dimension equals the number of conjugacy classes of G, and therefore now that the number of irreducible characters or number of irreducible representations up to isomorphism is equal to the number of conjugacy classes of G. Okay, that follows now. Okay, next time what we will do is the following. We will do some few corollaries. I will do some examples of character tables, what are called character tables. So essentially these are, the representation is determined by the character, so you make a table of all the irreducible characters. You write them in a standard form in a table, and that will give you all information you need to know about representations, irreducible representations of over complex numbers of a finite group. Okay, thank you so much.